Hi and welcome to this fourth clip in our Kinetics video series, and in this one we're going to look at the Arrhenius equation. The Arrhenius equation is a derivation of a number of theories which brings together an equation which helps us to calculate the rate constant for an equation, and it's something called the Arrhenius equation, and it's A, which is the Arrhenius constant, with a natural E, whereby the power of E is minus EA over RT. A fairly complicated looking equation, but as we say, A is something called the Arrhenius constant, something which a question may ask you to evaluate via rearrangement of the equation and substitution. EA is the activation energy, R being the gas constant, which you would typically be given in a question paper, 8.31 and so on, and T would be the temperature for these values being given in Kelvin. If we look at the equation, we see we have essentially two sections to it. We have A, which is the Arrhenius constant, or something called the pre-exponential factor. This relates numerically to the frequency of collisions that have the correct orientation, and is largely just a figment of the reaction which is occurring, and it's unaffected predominantly by temperature, so it's a fairly constant value. Whereas E to the minus EA over RT, which is the remainder of this equation, is this section of the equation is one which represents the fraction of the molecules that have the activation energy, or the minimum energy required to react. And normally what we see here is the relationship between both the activation energy and subsequently the temperature. In here, if we were to decrease the temperature of a reaction, so we made the temperature smaller, so if we were to decrease the temperature, the bottom line of the fraction, so minus EA over RT, would get larger. If minus EA over RT is to get a larger numerical value, once we put it into the equation, the E to the minus larger value would therefore become smaller overall, and this would therefore lead to a subsequent decrease of the rate constant. And as we know, as we decrease the temperature of a reaction would subsequently slow down. And vice versa, if we were to increase the temperature, that would lead to minus EA over RT becoming a smaller value. And if that becomes a smaller negative number, this means that the E to the minus smaller value would subsequently become larger, leading to the corresponding increase in K and subsequently the increase in the rate of that reaction. And so numerically, this brings together a lot of knowledge that you previously had at GCSE, knowing that temperature will increase the rate of a reaction. But we can see that in this situation, because we've got E to the minus a power, relatively small changes in T can lead to subsequently larger than expected increases in the rate constant and subsequently rate, which means the effect of temperature change on reaction rate is usually much more substantial than a corresponding concentration change was, for example. Doubling the concentration will double the rate, perhaps, for a first order reaction, whereas relatively small changes in temperature can lead to significantly larger increases in the rate. Now, the use of the Arrhenius equation is usually a way of calculating the activation energy. Typically, the activation energy may be the subject of a question. And if we have the Arrhenius equation, what is usually required is to take the natural logs of the equation. So if we were to take the natural log of both sides of the equation, what we would see is that via log laws, ln k on one side of the equation would become equal to the natural log of everything on the right hand side of the equation. But mathematics will tell us that if we have two values multiplied together and we subsequently take the log of those, we can separate that into its two component multiplication halves, both of which are then added together. The natural log of something which is e to the power essentially cancels itself out. It's the inverse function of each other, which means that the ln k value is then equal to ln a plus minus ea over rt, just as a value. We've now lost that e function within the equation. But if we were to again then simplify out our equation here, we end up with the Arrhenius equation written in a more linear form here. And this is now taking the form of a y equals mx plus c equation, essentially. We've got some differences in signs, but essentially this is now an mx plus c, and this mx function is very important because this is the way in which we can then subsequently evaluate what the activation energy is. And we do that by plotting a graph of ln k versus 1 over t. So we would put ln k on the y-axis and we'd place 1 over t on the x-axis. What this does is if we were to then subsequently separate ea over r multiplied by 1 over t, which is a different way of writing that sum there, our 1 over t aspect of our equation is our x term, which means our m, which is typically the gradient then of a y equals mx plus c graph, has become equal to ea over r. If we can then plot a graph, as I say, of ln k versus 1 over t, which I will quickly sketch on this next page. So if we start afresh here and rewrite our equation again, we're going to take ln k equal to ln a minus the activation energy over RT. And again, just to reiterate, what we're going to actually plot is 1 over t, which then equates the gradient of that equation graph that we're then going to plot as EA minus EA over R. So we would plot that. It wouldn't be a surprise to see negative scales sometimes, and we would see ln k, as we say, on the y-axis, and we would plot 1 over t on the x-axis. Again, sometimes you may want to scale your 1 over t value to make it nicer looking numbers that you can plot. And we would then get a straight line, y equals mx plus c, whereby a calculation of the gradient by taking dy by dx, or rise over run, however you term the gradient. So we would take dy by dx, And if we were to calculate the gradient of that graph, that would give us EA over R. It would be a negative gradient, which means if we were then to subsequently change the sign of the gradient we've just calculated, the gradient of the line multiplied by the gas constant, 8.31, will give you the activation energy for that reaction. Good question in an exam, asking you to plot a graph, obviously, and some calculation of the values to plot, and then the subsequent extrapolation of the activation energy. So quite often a heavy mark scoring question, but that will show you how to calculate that. And typically the Arrhenius constant, as we say, is a way of calculating the activation energy, and using some log laws and some drawing of some graphs allows us to calculate that and bring those together, and using the rate constant as well. We'll see you in the next question, in the next video, whereby we will look at the relationship of all of this together and see what the rate equation tells us and how we can then use that to establish how a reaction proceeds during its pathway. Thank you very much, and I will see you in the next one.